Hello and welcome to the Matter Over Mind podcast, or MOM, as I continue to call it. I'm Stephen Mather, and I'm a business psychologist with a bachelor's in psychology and a master's in organisational psychology from the University of London.
And I'm Thomas, an experimental physicist at the University of Oxford with a master's degree in theoretical physics, working towards my PhD in atomic and laser physics.
Cool. So we say that at the beginning of every episode to, I guess, demonstrate our credibility. But are you bored with saying all that?
It's a little bit, yeah, it doesn't roll off the tongue.
So, I don't know. I'm the psychology one and you're the physics one. Maybe that's what we should go with in the future. All right. Okay. So that's it. Right. So today, one of my favourite podcasters is Sean Carroll. I really love his Mindscape podcast. I listen to it every week. Well, most weeks. Most of the topics are really right on my street. But he has this habit of sort of just referring to the Lagrangian. So he'll say something like, oh, so in this case, it's just a case of the Lagrangian. And then just move on. And, I'm sure I should know what the Lagrangian is, but I feel like I don't. And, I'd love to know about that. So I asked you about that, and you sent me a video because you said perhaps you needed a bit more sort of underpinning knowledge first.
Yeah.
So you sent me a really pants video, Thomas, which was about the Higgs boson. It's like a cartoon for 5-year-olds.
It was true. It was either this little cartoon, very hand wavy, not really saying a lot, or Sean Carroll doing his thing. So I didn't want to just end your lecture. So I thought,
Yeah, I listened to it twice. And yeah, there's quite a lot in there actually that I did get from it. So it wasn't that bad. But yeah, it's a bit sort of lower the standard that I'm looking for in video. Content.
Okay.
But anyway,
I'll keep that in mind for next time.
Yeah, keep that in mind. Thank you, son. All right. So anyway, you're going to talk about. You're going to help me understand the Lagrangian. So by the end of this little podcast session, I really hope I've got a bit of a handle on when Sean says this is now the Lagrangian, or you'll use the Lagrangian, or whatever. I understand what that means, and in getting on that journey, maybe you teach me some stuff about the Higgs boson as well, a little bit anyway, and.
Yep.
That might be useful. Okay, so tell me, where do we begin?
Okay, so I'll start as I did kind of last time with a dictionary definition, if you will, of what the Lagrangian is.
Good place to start.
And this is straight from Wikipedia now. Okay. Lagrangian is a functional whose extrema are to be determined in the calculus of variations. So that should answer all your questions.
That's as clear as mud. Yeah, I'm a big fan of Wikipedia, by the way. I actually contribute to it. I started to pay my £3 a month
nice.
Because I think it's it's one of the few places that you can go on the internet where I'm not saying that it's all 100% true on Wikipedia, but at least they try, don't they? So so yay Wikipedia, but I didn't understand a word of that, so that's not helped me very much.
Okay, so I'll give it a bit more context. So, in general, you probably come across just in the world take the path of least resistance. That's sort of very common saying that people say. It's basically saying that a Lagrangian in a real sense now it's effectively an equation that is an energy balance. So one common example that maybe the first way you learn it when you go to university, it will be the difference between the kinetic energy, or the energy of things in motion, and the potential energy. So a bit of context of what potential energy is. So one of the ones that you'll probably learn about first when you delve into physics is gravitational potential energy. Okay. So a way to describe this, if you have a pencil on a table, it's just going to sit there. It's not going to do anything. As I raise it above the table, the higher it gets, the more potential it has to gain speed when I drop it. Okay. So as I drop the pen, it travels down, it gets faster and faster and faster. So it gains kinetic energy as it lowers in height. And because it's dropped in height, it's lost potential energy. So a way I think about potential energy is the energy a system could have once it's begun. So, like I say, if you have your Lagrangian for that system, the pen above the table, you'll have the kinetic energy, which initially is zero. It's at rest. There's pencil has no energy, but it has potential energy. And then when I drop it, it falls down. Its kinetic energy grows as its potential energy decreases.
Okay, so let me just repeat that back for my own understanding. You can tell me if I've got it right. So we've got two types of energy here. We've got potential energy and we've got kinetic energy.
Yep.
Potential energy is, as it sounds, the potential to produce energy in the world, I suppose. If you hold something from a height, as soon as you let go, it's going to start doing something. It's going to be energetic in some way, but as long as you're holding it, it's only potential. Like one day I could be a movie star. That's my potential. And until I actually, start making movies, I've only got potential.
You can think of it as stored energy. If I compress a spring while I'm holding it, obviously the spring isn't doing anything, but it's still compressed. It has internal energy. It is stored energy. When I let go, the spring expands and shoots out. Yeah. So think of it more like that. If I hold the pencil over the table, imagine a gravitational spring that's been stretched. And then when I let it go, it wants to return back to its equilibrium.
Yeah, so we've got two types of energy. We've got this potential energy, which we've just been talking about, and we've got this kinetic energy, which is when the object is actually being energetic in the world. And as that kinetic energy increases, the potential decreases. So the two have this kind of relationship. And that's obvious, really, because as it gets closer to the floor, then it's got less to fall, isn't it? So it's got less potential, but more kinetic until it stops on the floor. And then it's got no potential or kinetic energy. Is that right?
Yeah. So at the instant of impact, of a fraction before it hits the ground, that's when I guess it's got minimum potential and maximum kinetic. So think of potential as a reservoir. The kinetic energy can grow as much as there is potential. It's sapping out of that reservoir. So to keep with your sort of movie star analogy, before you start your movie career, you have all the potential, but none of the momentum. You've not done anything. The more famous you get, the less fame there is to get, if that makes any
sense. Yeah, absolutely. Get that.
So it's kind of like that. So the more kinetic energy you have in this what I'm going to call closed system, the less potential there is, because I've sapped away from that reservoir.
Okay. And you're suggesting that the Lagrangian, which obviously I want to know more about this, but the Lagrangian is something to do with the path from potential to kinetic, I suppose, or as this pencil falls, that's the Lagrangian, that's the path of the energy as it goes from high potential to kinetic through to no potential again.
Yes and no. I'll tell you, thinking of it as a path is actually a pretty intuitive way of thinking about it. That's quite a good grasp there. So the definition of the Lagrangian in this particular context is the kinetic energy minus the potential energy, and how you actually engage with this Lagrangian, this sort of energy balance equation, is you would put it in what's called an action. So I mentioned an action last time, and think of your action as a trajectory, a path. In this case, it's a path through time to get the dynamics of the system. It can be in space. If it's space, it becomes a Lagrangian density for basically bookkeeping reasons. But
so our pencil, that's moving through time and space, isn't it?
Yes. Yeah. So there's a bit of a distinction. So a Lagrangian, as it is treated in classical mechanics, which is the physics of basically every day. So, bulls rolling down hills, cars driving along, and whatever else. That's classical mechanics.
Okay.
Once you get into relativity and even quantum mechanics, then the rules change a little bit. But for classical mechanics in our everyday world, it's by looking at the energy change between the kinetic and the potential, you can derive the dynamics of the system, so how the system will behave as time moves on. So, and another way of thinking about this is it finds the path that costs the least energy. So you've probably heard this, energy can't be created or destroyed. sort of thing. So if I throw a ball across the room, it's going to take a parabolic trajectory. It's going to take an arc over this, across the room that I've thrown it in. Now, the path it takes can only cost the same amount of energy as I've input. Right? It can't start doing circles, or it can't start floating around or whatever else. But if it's a heavy ball and I throw it, it's going to have to follow a very specific trajectory that matches the energy I've input.
Right.
And that's kind of how the Lagrangian determines things. You put your Lagrangian in your action, which is kind of like your path, and your Lagrangian actively dictates the path required to use the least amount of energy, or to use up all the energy you've input into
that's available. Right. Okay. So if I'm going for a walk with the dog and I've got a ball to throw, a tennis ball, and I throw the ball, I put a certain amount of effort into that throw. So that's the energy that I'm putting in to the throw of the ball. And then just before I let go of the ball, is that where the potential energy is highest?
Yeah.
And then I throw the ball, and at that point, the kinetic energy goes through a period, I suppose, where, it's going up, and so there's less kinetic, and then it's coming down, more kinetic. And as that happens, then this relationship between the potential, which is what it could get to, and the kinetic, which is where it is at the moment, that sort of plays against each other as it's going on this arc, as I've thrown it for the dog to go and chase. But obviously, logically, it can only, if you add up all of that energy, potential and kinetic, it can only have as much in as I've thrown with my, old man arm. Now, okay, I get that.
Yeah, so, that's a slightly other way to think about it. If I drop a ball, if it starts falling upwards, you've added potential energy. That can't happen. If I drop a ball, it's going to fall down. If you throw a ball, it's going to travel in this arc. And the arc, if you were solving a problem to do with someone throwing a ball traveling in an arc, you probably wouldn't use Lagrangian mechanics. It's a bit of a sledgehammer to solve that, but that's what it's telling you. It's telling you your energy path, if you will, through space and or time, and it has to be minimized. So it's
sorry. So let me interrupt a minute, because our listeners might be saying, okay, but what is Lagrange? What is Lagrangian? What does it mean? I think it's the name of a person, isn't it?
Yes, yeah. So there's a guy, I can't remember his first name. According to Wikipedia, it might be Joseph Louis Lagrange, and I'm hoping it's the right guy. But yeah, Lagrange is a name, and his name crops up quite a lot in physics and maths. He was quite a prolific character. Lagrangian mechanics has kind of dictated how we do almost all of physics. So that's
no wonder Sean Carroll thinks we should all know it, really, but I don't. So.
And to be honest, there will be some people that do a physics degree that if they've not taken any theory modules, they probably won't really encounter the Lagrangian. So there may even be some physicists in the world who don't. I would hope if they're an active researcher, they probably should know what it is. But maybe if they finish at undergrad, maybe they've not encountered it, which I think should be mandatory. But that's just my opinion. But yeah, so a Lagrangian, it's an energy equation that needs to be minimized such that when an object travels through space and time, it follows the path that uses up only the amount of energy it's been given.
Great. Okay. And is it essentially a formula, basically? Is that what we're talking about?
Yeah. So
it's a scientific formula.
It's usually denoted the letter L. It's a capital L. L is the Lagrangian, and it's kinetic energy minus potential energy. There are more complicated forms of it, but in the most simple form of this. Okay. And if you set that to 0, you're basically saying, I want to follow the path that costs the least energy. Yeah. And the only way for that to be true is if the potential is equal to the kinetic.
Okay, brilliant. So what's that got to do with the Higgs boson? Why was I listening to a worm talk about the Higgs boson on a video?
Yeah, okay. So it probably feels like my description of a Lagrangian is completely irrelevant to anything to do with particle physics or even gravity. I'm just using some caveats. I'm kind of throwing at you just some to specific observations, it probably seems meaningless. But so before we get to the Higgs boson, still, I'm going to tease this for a while. It's quite a long journey. It turns out that the Lagrangian has another special property, other than basically just being an accounting term for making sure no energy is gained or lost where it shouldn't be.
Yeah,
it has this other interesting property, and this was derived by a mathematician and physicist called Noether, or Noether. I'm not too sure how to pronounce it.
Not Nutter. Sounds like Nutter to me.
No, it's got one of those E's with the dots on it.
Okay.
Yeah, so she was quite a famous mathematician of the time. I think it was early 1900s, maybe. I could be wrong. But yeah, basically, she put out this idea that. Hold on. Before I get to that, there is something else more important. I'm jumping ahead. I'm getting too excited. Noether's theorem is very exciting. But before we get to that, back to Lagrangians for a second. So before we move on from that, one of the cool things about Lagrangians is, so usually when you first learn physics, you learn about it in terms of balancing forces. I push an object, it moves some. And you learn Newton's laws of motion. So you've got, for example, I won't bore you with what they specifically are, but one of them is if I push something, it accelerates, it moves.
Yeah.
When you start to deal with problems that have more than one or two objects, equating forces becomes very difficult. Imagine you've got some billiard balls cracking into each other. If you have one or two, it's very easy to figure out where they're going to go. There's a whole, school of mathematics to describe exactly how two hard spheres hitting into each other, what they're going to do. But if I throw 17 billiard balls now, and then I start to try and work out what's going on, it's very difficult to map out the what direction that the forces are going in for each ball, what's the net direction of the force, etc., etc. Whereas if I just say, cool, we have some billiard balls and they have an average speed of, 2 miles per hour each, well then I can very easily add up the total kinetic energy of the system, and I can also work out the total potential energy of the system and take the difference of the two, do my little minimization trick where I set everything to 0, and now I have the dynamics of the system without even having to care about, the Red Bull is traveling 12 degrees northeast or whatever. So using Lagrangian mechanics in this same way, whereas I wobble this action, this path, and set it to 0, and then that kind of balances my energy. With this, you can derive Newton's laws of motion. So Newton came along, he kind of states these 3 facts. These laws of motion that kind of everyone goes off and they're pretty good. But then a little bit later, this character Lagrange and his friend Euler, which also appears quite a lot in maths and physics. So hold on, let's do this calculus of variations, as it's called. Wiggle around some paths, work out some energy balances, and then bam, just kind of out of conserving energy, just falls out Newton's equations of motion. You can, by looking at the energy exchange in a system, you can derive, I push something, it moves, which sounds very trivial, but in a very fundamental way, it kind of it changes the point of view. So instead of talking about it in terms of, well, I'm pushing this, I'm adding energy to this, I'm pushing it, and it's moving, it's talking in a more general sort of, I guess, systemic sense of, this is the internal energy. If I mess with it with some external energy, this is how the system evolves. And with it, you can derive sort of real tangible dynamics.
Okay.
That's kind of how thinking about energies can then still output information about forces and regular dynamics. Like I say, you can use an energy balance essentially to get back, how forces interact. If I push something or I pull something, how the state's going to move. This is just, I guess, the next level of trying to break down your system into more fundamental parts. So anyway, that's the Lagrangian. It's an energy balance basically, and with it you can work out real world dynamics. Okay, so that's that. Before we get to stuff like particle physics and the Higgs boson, which we will get to, there's a little bit of a tangent. As I mentioned before, Noether's theorem. And so you'll have to bear with me because this may get a little bit abstract. But what she said was, or what she discovered rather, was for every symmetry that's conserved, there exists a conserved quantity. Now, so by symmetry here, there's a little bit more to it than just what you may think. Obviously, if I have a circle and split it down the middle, I can say that's symmetric. Left and right are the same. So imagine now I have a disk flat on the table. So it's symmetric, yeah. If I cut it in half or cut it in fours or whatever, all the pieces are symmetric. So that would be one description of symmetry, but there are multiple. So if I now rotate, if I put my finger in the middle of the disk, the DVD or whatever, and spin it around, and suppose there's no picture on the disk, well, it doesn't matter how much I rotate it by; it's still the same. You won't really you won't know how much I've rotated it by, right? If I just spin the disk around, you can't tell me if I've spun it by 10 degrees or 360 degrees. It's just a circle that I've rotated around it.
Okay.
So that's a rotational symmetry. So that's another example of the symmetry. Now imagine you have a really big table, a really flat table, and again it's just smooth and it's not going to painted white or whatever. And I argue within the boundaries of that table, as long as I don't leave the table, it has what's called translational symmetry. If I put something on the table and move it around, the table is effectively constant. The table doesn't change. So the table has what's called translational or spatial symmetry. It's symmetric if I move left, right, up, or down. So that's a bit of an extension to what you may think of when I say symmetry. And it turns out for each of these symmetries that exist in a system, there exists what's called a conserved quantity. So how before I said energy has to be conserved, potential energy must equal kinetic energy. In this way, if I have a translational symmetry, so like the table, if I move around, then the momentum of the system is conserved. So that's kind of another way of saying that is, if something's not moving, it's not moving, and if something is moving at constant speed, then that's kind of equivalent. If something's moving at constant speed, there's no forces acting on it. It's just moving at a constant speed. It's not accelerating or slowing down. There's no forces involved. Equivalently, if it's stationary, there's also no forces going around. So it turns out that property kind of coincides with this translational symmetry. But
yeah, okay. I'm going to stop you there. So let me see. I need to get my head around this. So first of all, you lost me a bit around the different types of symmetry. So I think everybody listening will know what we mean by sort of normal symmetry, both halves, equal, as if you like, or a mirror image of each other. You said then that like a disc, let's say a CD or a DVD, if you were to rotate that, then it's still symmetrical. Why is that still symmetrical?
Okay, so imagine you're looking down at your disc, you're looking bird's eye view of the disc, and I put a little line on it, and it's the line at 12 o'clock. I rotate it some and then stop rotating. You know how much you rotated it because the line is now in a different position. That little nut. Okay, so that's not rotationally symmetric because I've rotated it and it's different. However, suppose it's an empty disc. It's just a plain disc, no image, nothing on it. I'm looking bird's eye view at it. If I rotate it by some amount, and then I say, have I rotated it? You can't tell. Can't tell. It's exactly the same. The system is effectively unchanged by me rotating it. That's an example of this system is symmetric under rotation. Or when I rotate it, there's no change.
Okay, great. So when we get to the table now, where you're sitting at the table is square, is it?
It doesn't really matter. It's just a really big table. Yeah.
Big table. You've got an object on the table.
Yep. I'm rolling the ball around. To the ball that I'm rolling around on the table, as long as I never reach the edge of the table, the plane that the ball is rolling around on is unchanged.
So if you don't see the edges, if you had a camera that was looking at, if you got your camera phone out, and you took a video of the ball rolling around, but didn't get to see the edges, is that what you mean?
Yeah. So imagine an infinite plane. I use the table just to sort of give an analogy in the real world. But yeah, imagine you have an infinite flat plane. It's white. There's nothing. If I run around, I can't tell if I've moved or not. I'm effectively in the same place.
So it's like in those films where somebody goes to heaven and it's all white.
Yeah.
Everywhere is white.
And they run down the road and the changes. Yeah, exactly. Yeah, so that's unconditional symmetry. There was in translating my position, in moving my position about. There's no change system. Yeah. Okay. So yeah, each one of those has an associated conservation, and energy conservation is when you have a temporal symmetry. So if as time moves on, time flows forward. If nothing changes but time is moving forward, or in principle backwards, but for now just forwards. If time is moving forward and everything is just stagnant and nothing changes, then energy has been conserved. There's no energy change now. So this idea of a thing or a property being unchanged when something is happening corresponds to an associated conserved quantity. That idea gives rise to our current description of particle physics. It seems like a big jump, and it is a big jump. There's a lot of stuff in between, but that very basic principle of if I interact with a system and in some particular way it remains unchanged, then there's now a sort of measurable actual quantity that has to have stayed the same. With this idea, you can build up a lot of complicated maths that can then be used to describe particle physics. Okay, so yeah, each symmetry in a system corresponds to a conserved quantity. So with that in mind, again, you'll have to bear with me. I'm going to make a massive leap now, but let's talk about the Higgs boson a little bit. Let's give a little bit of, I guess, real world physics.
We need a bit of sugar. You need a bit of sugar. So okay, I appreciate there's probably a big chunk that you'd like to tell me about. We'll save that for another time. Mm-hmm. And so there might be a little bit of disjunction between where we've got so far and the Higgs boson. And if there is, then we will close that either at the end or in another episode. But you made me watch this stupid cartoon, so I need to understand a little bit about what the Higgs boson is all about.
Okay, so before we get to the Higgs boson itself, let's look at the Higgs field. So this will kind of include that big jump we've made. So you have now your Lagrangian, you have your kinetic energy. So particles have an energy that they're moving at some speed. Yeah. And you have the Higgs potential. So, the Higgs potential or Higgs field, this kind of gives rise to particles with mass. But how is that? So I mentioned before, I've mentioned loads of times now, you've got a ball on a hill, I kick it, it rolls down the hill, there's a change in potential, there's a slope going on, and that sort of, that has dynamic effects on your system. So the Higgs potential, this, or sometimes called the wine bottle potential or Mexican hat potential. Okay. It's exactly that, at the bottom of a wine bottle, you've got the little thing to put your thumb in. You've got this, this sort of this bell-shaped Eshker with a little troughs out the side. Now, this potential is kind of interesting because it's kind of got a rotational symmetry. But if you look bird's eye view down at a sombrero or whatever, you can rotate it some in the same way as a disc, and you won't know I've rotated it. So there's an interesting property there. You get what's called spontaneous symmetry breaking, which I'm not even going to bother delving into because you'd probably need minimum of a master's degree to understand what that means. So I won't bother. But what's interesting is when you look at your Lagrangian, it can tell you information about how particles interact with each other. It can also tell you how much charge or mass they should have based on prefactors they have on their terms within the Lagrangian. And it turns out, if you're on the top of the sombrero, the top of the sort of wine divot, you're fine. But if I wobble, if I interact with the Higgs field in any way, the Higgs potential, if I perturb it, if I kick the ball off of the tip of the sombrero, roll down. Now there's this perturbation in the Higgs field. This particle interacting with the Higgs field is making it roll down this hill. And what this results in is it kind of results in these additional particles being formed in here, in your Lagrangian. And these additional particles have these prefactors. They have these weights holding them down. And effectively what's happening here is, what this is telling us, the thing sitting at the top of the sombrero, it's not interacting with the Higgs field. And if you look at the equations, these things have light speed, so that it's light. It's okay. Or rather, it's something at light speed, which must mean it has no mass. If you remember from the other week,
from our last light speed episode.
Yeah. You have light speed, you have no mass. But when it interacts with the Higgs field, when someone gives the ball a kick and it rolls down the tip of the sombrero, it lands in this trough. You have this additional term kind of cropping out that kind of falls in with a prefactor to signify the fact that it's been wobbled around a little bit. Yeah. And this prefactor now basically says that this thing that was a light speed particle now has a weight attached to it, and it's slowing it down, which means it now has mass. If you're traveling less than the speed of light, you have mass. So by interacting with the Higgs field, and you can, and like I say, you can discern this from the Lagrangian by wobbling the potential, by giving it a little kick. It turns out, you kind of get these additional things forming which have weights to them, and these weights hold them down. So the Lagrangian, I guess what it's trying to tell you here is, when you stream a particle and it interacts with the Higgs field, to balance the energy equation, to keep everything on, in check, you have to have mass now, because you've kind of interacted with this medium and you've lost some speed. And the only way to do that is to have mass. It kind of sounds like a bit of a cyclic argument. But yeah, that's I said way back at the start of the podcast, if you wobble the Lagrangian or you wobble the action, it has to be minimized. It has to kind of, accounting has to be done. You can't add or subtract. So when you wobble the Higgs field, I kick the ball down the sombrero. I've added some energy into the system now, or something has changed, and to balance that, it has to be taken from somewhere else, and then you get these kind of weights tacked on to these light speed particles, pulling them down. So it probably sounds like it's completely unrelated to what I'm saying. But it all kind of falls down to, if you wobble the Lagrangian, if you vary it, it has to keep its minimum. It has to be minimized. Yeah.
So let me try and put it into words that I would kind of understand. So this Higgs field, I think we might have spoken about it briefly last time. This is like the all-pervading field in the universe. Is that right? There's kind of everywhere.
Well, technically, or at least in our current description, every particle, everything is infinitely spanning. And the Higgs kind of permeates everything, but so does the electron field. So does the proton for everything. So
we've got all these fields. Imagine in the universe, we've got all these fields. You did a good description last time on the last episode to help me understand like a magnetic, electromagnetic field. And we talked about that for a bit. So it's like that. There's a field everywhere for all of these different particles. Mm-hmm. And I guess I would describe it this way, that in any part of that field, there is potential for a particle to exist.
Yeah.
And the Lagrangian, the formula you've been describing, predicts that some bits of that field are going to end up forming mass. And the Lagrangian predicts that, tells you where that's going to happen. Is that right?
Yeah, kind of. So some, I guess, slight additions to kind of help explain a little bit. So all these fields are kind of everywhere, and I keep mentioning about wobbling this action or perturbing this Lagrangian. So as described by a current model of particle physics or in quantum field theory, which is sort of current fundamental theory, you have these fields and disturbances in these fields, wobbles in these fields. Imagine you've got a really taut sheet, or like a bed sheet. If I crease it a little bit, It's flat everywhere, but there's this crease. That's a perturbation. I have my action, which is my trajectories through my space. I have my Lagrangian, which describes my energy. There's a bunch there. So someone's kicked it, someone's wobbled it. That little collection of stuff, for example, the electron field, suppose you now have a perturbation in the electron field, that little bunching of the electron field is an electron.
Yeah, and that was one of the, when I watched a few videos accompanying your cartoon video, that was one of the things that really I found really interesting, because I think in our pre-talk, we did discuss this, that in my mind, when I went to school, it was like you've got everything's made up of atoms, and then atoms are made up of electrons, neutrons, and protons, and then two out of those, electrons and protons have stuff that make them up. So
you've got electrons are essentially fundamental.
Sorry, not electrons, protons and neutrons. They also have little particles that make those up. So you get this feeling that you just got big balls, smaller balls, even very small, much smaller balls, but they're all particles. But in a way, what you're describing is a particle isn't this very clear, it sort of exists like a ball bearing. It's a part of the field that the electric field, let's say, that, as you described it, there's a perturbation in that field, and that forms a little nodule.
Yeah.
And that's your particle.
Yeah.
And that's really interesting, because it kind of explains, well, for me anyway, that just gives me a new insight into that. Okay.
So that's, why I keep going back to, I wobble my action, I perturb my Lagrangian. Why that's so important is it's only when you vary this stuff, it's only when you perturb this stuff that anything really happens. If you didn't do anything, everything's just kind of stationary. Now obviously there are vacuum fluctuations, but I'm talking more in a more general sense now. This just, if I don't do anything to a house, it's just going to basically stay there and do nothing, right? If I leave the fields alone, they're not going to do anything. If I now kick the field, kick the potential, now cause a slope such that something can now happen, you get these bunchings, you get these creases on your electron or proton or whatever field, and these things can now interact in a particular way. And it turns out when stuff engages, when you have a bunching of the Higgs field, that's when you kind of get these things streaming. The photon field now engages with it, and then it kind of slows it down. An example of it's been sort of an analogy that you'd normally see if you're looking up on what the Higgs field does is it's kind of like they talk about it like you have these billiard balls whizzing around, and then suddenly they hit honey or they hit treacle or something, and it slows them right down. Traveling through the Higgs field is like wading through mud. It kind of slows you down, and that kind of makes you that gives you, I guess, it makes you massive. It feels like you're massive now.
Yeah.
With this.
Okay. All right. Well, I think that's all you can take, is certainly as much as I can take. Thank you very much. I mean, that's tricky. I hope that everybody's been able to get something out of that. Thank you very much, Thomas, for guiding me through what seemed like a really easy question. What's the Lagrangian? Well, that's the Lagrangian, Stephen. Okay, great. I think there's still more to come on the Higgs and obviously the Higgs boson as well, which is something we haven't really talked about. So we need to cover that. That's a very well known phrase, but I think most of us probably don't understand what that is. But we've now built a bit of a foundation for that.
Yeah. So
we probably need more than one listen. I know when I edit these, this is only the second physics one we've done, but when I edit it, I learned more the second time, so you can listen to it more than once. That can kind of help. And obviously get a bit of feedback from you as listeners. We are still finding our feet with this, so let us have a bit of feedback about what's easy, what's not, and some of that comes through from our explanations of things, depending on who's doing the explaining, and then other parts come through the editing. So obviously that's the bit I do as well. So you can give me a bit of advice about that where that's not working. Cool.
I'd like to say that one of the main takeaways, I guess the reason why particularly I was interested in explaining a bit more about the Lagrangian, what was kind of to shed light on basically how physics is done, really, how theoretical physicists, especially in particle physics and in gravity research, how they think about things. They rarely think about things as forces interacting or like you say, billiard balls. It's more they think about it in a general, how does the energy of the system evolve and change? And maybe in sort of, I don't know how much this is talked about in sort of the podcast that you listen to, but this sort of understanding of what a Lagrangian is and why energy is such an important thing, or energy balance, or entropy, or whatever. Hopefully, this has kind of given a bit more to a sort of like an insight to maybe why they might describe things in particular ways or something, right? Yeah. It may seem weird to think about energy when you could just think about, well, I can see the ball rolling. Why do I need to think about its kinetic energy or whatever?
And I think the other takeaway, which is probably a philosophical question for another time, but the emphasis is on the maths and what the formula is telling you. So, you talk about wobbling the Lagrangian, that you're not actually wobbling anything physically. You're changing something, or you're doing something in the formula, aren't you, really, that makes that happen. So it's like, you go from, like, a layman like me thinks about maths as describing what you're seeing. But at this level, you're really using the math to tell you what you're not seeing, if that makes sense.
Yeah, exactly. I mean, a lot of, well, especially cutting edge research, it's, well, I don't want to say guessing, but it's very well informed guesses to, okay, I think this will happen based on, whatever else. And then experiments gets done. Cool. Does this match what so-and-so wrote down in their maths? Yes, it does, or no, it doesn't.
Yeah.
If it doesn't, is that because their maths is wrong, or because they've maybe missed out a term, or that they've not quite used the right potential, or actually this curve is actually a little bit more bent than it is straight, or whatever. And that can, by looking at the maths down the line, it can sort of have detrimental effects if you use the slightly wrong form of potential. I mean, that's one of the main things of my research at the moment. Is there's a description of how things work. Yeah. There's the simplified description that logically makes sense, but the simplified description doesn't quite match what is observed in experiment. Okay. So I'm trying to see at what point in the simplifying of things down it went wrong. Basically. Okay. So the maths is very informative. It's not just we're kind of making up equations and then seeing what happens. There is logic behind it, but the maths very much does dictate. It's a description. As opposed to real life, it's kind of a toy model.
Yeah. Right. Okay. Cool. All right. Well, thank you very much. So next time on our next episode, I would like to talk about consciousness from a psychological perspective, because this is a big hot topic in lots of the sciences, and it's a real overlap between psychology and physics. So I think there's a real rich vein here where we can get into looking at this question of consciousness in all sorts of different ways. It's also big talked a lot about around AI systems and, what can we expect consciousness, and would we know it if we saw it, and all those questions. Fascinating. I find it absolutely fascinating. But I want to come at it first from a psychology perspective and think about what we mean when we talk about consciousness. Mm-hmm. And then, at some point we can start to get into the more physics side of that as well. So I think that's a potentially interesting one. Now, I've had an idea, which I'll float it here. We may well keep this in the conversation on the podcast. But I was thinking of, like, most podcasts, they have one every week or one every fortnight or two a week or whatever it is, and they release one each time. I was wondering whether we go for the dyad approach, which would be a unique way of doing our podcast. But because each one is, so every other one is very different. So we have a very heavy physics podcast, and then we have a very psychology podcast. It might be one week that you think, oh, I can't get into the physics of that, let me listen to a psychology one. Or that you think, oh, psychobabble, not for me, thanks, Steve. I want to listen to Thomas. And I was wondering whether we release 2 episodes every 2 weeks. So we release a physics one and a psychology one every 2 weeks. So they come in pairs. Then obviously people can listen to them in whatever order they want, and they can still listen to one a week, but they're there, they're both there, and they can decide which one of those two they want to do. So we release them as dyads rather than individual podcasts. What do you reckon?
Yeah, that sounds great. Yeah.
I floated that. You like it. Listeners, tell us what you think about that. I mean, essentially, it can make no difference because you decide when you want to listen to them anyway. But it just means they're both out there. So you've got a physics one and you've got a psychology one. So if you've listened to this episode, then already in your inbox or in your podcast app should be the psychological approach to consciousness, part one. Part one of many, I think. We'll get into that in lots of episodes. So yeah, just a heads up there that sounds quite an interesting way of doing it, I think.
Yeah.
Cool. All right. Well, I've been suffering from a cold, you might have noticed, and I've been sort of sniffing and sneezing in between my comments. So I'm going to go away now and get myself a glass of hot lemon or something and talk myself up to bed. Thanks, Thomas. Thanks very much for your help with that today. Thanks, listeners, for listening. Don't forget to tell people about the podcast, subscribe, like, and all those good things. And we'll see you next time. Bye for now.
Goodbye.